This is the DC power supply we use in the Introduction to Engineering lab. There are many available power supplies on the market. This particular model is the Tenma digital controlled DC power supply. This digital controlled DC power supply is capable of putting out 30 volts at 3 amps. In some labs, we can connect batteries to our circuits very conveniently. A battery, though, is a fixed voltage source. The main purpose of a variable DC power supply is to give us flexibility in how much power we supply to our circuits. This allows us to control the voltage and current supplied to our external circuit. Now let's have a look at the front panel of the power supply. On the front you will see the big blue button, which supplies power to the device. In other words, this is the on and off button. Once the blue power button is pushed, you will see two displays light up. The display under the letter A, which is short for amps, is for current. The second display under the letter V, which is short for volts, is for voltage. The device is not connected to anything, so the current meter is displaying zero current. On the bottom right of the front panel, you will see three input jacks colored red, black, and green. Red is for positive, black is for negative, and green is for ground. We will only be using the positive, red, and negative, black jacks. This device has two modes. We will primarily be using mode 1, but I will cover both modes, just in case you accidentally activate mode 2. How to tell which mode you are in is to notice how many LEDs are illuminated. Currently there is only one LED illuminated under CV. CV stands for constant voltage. If only one LED is lit under CV, that means you're in mode 1. If you turn on your device and you see 3 LEDs illuminated, this indicates you're in mode 2. Here you see one LED under CV, one under the ones position in the volts, and one under the tenths position under current. When those 3 LEDs in red are illuminated at the same time, that means you're in mode 2. If you are in mode 2, press and hold the current and voltage knobs for a few seconds until there is only one LED illuminated under CV. If only one LED is lit under CV, that means you're in mode 1, and that's the mode I want you to start with. Notice when I rotate the front knobs, nothing happens. To adjust the voltage, I have to push in and release the voltage knob. When I do that, you'll see a blinking LED under one of the digit positions of the voltage. Here the LED is blinking under the ones position, right before the decimal point. Whenever that LED is blinking, I can adjust the number in the digit position above it. Right now you can see I'm adjusting the ones position of the voltage. Let's set it at 2.0 volts for now. If I push the voltage button in quick succession, it will change the digit position that I can adjust. Here I pushed it twice and it changed from the ones position to the tenths position. As long as that LED is blinking, I can adjust the number above it. Now when I double click it again, it moves to the hundredths position. While it's blinking under the hundredths position, that number can be adjusted. See how I can adjust the output voltage very precisely to a hundredth of a volt. Now this is a serious warning. One potentially dangerous aspect of this is if I push the button again, it moves to the tens position or the tens of volts range. That means with a very simple twist of the finger, I can go from very low voltage to very high voltage quickly. I can go from 0 to 10 volts to 20 volts and almost 30 volts with very little effort. So be careful not to adjust the tens of volts digit position. Another feature of this instrument is to limit the amount of current that flows into your circuit. This is a safety feature. While in mode 1, in order to see the current limit, you have to push in and release the current button. The LED will blink under the digit position that can be adjusted. Let's set the current limit to half an amp. Notice that this is displaying 0.5 amps. That means the current limit is set to 0.5 amps. In other words, in your lab experiment, the current will not go above 0.5 amps. Not that the machine is registering or supplying 0.5 amps of current. This number is completely independent of the volts that we supply. Again, this is a safety feature. The next step in this demonstration is to attach an external resistor to the power supply so we can show how these connections are made. This resistor is labeled 1000 ohms. I measured it with an ohm meter and it's actually 960 ohms. This particular resistor has an accuracy rating of plus or minus 10%. I'm going to make a connection to each side of this resistor. This will mean power is going through the resistor. We are going to use these banana plug cables to connect from the power supply to the resistor. I have attached alligator clips to the banana plugs. The color coding is a visual representation for the convenience of the user. The color does not matter to the instrument, but if we match the colors to the input jacks, it helps us clearly identify the proper connection. So let's use a red alligator clip coming out of the positive red terminal of the power supply. To be safe, let's turn off the power by pushing the big blue button. Now that the power's off, we can safely plug in the banana clips. The color of the cables also doesn't matter to the instrument, but again, it is a helpful visual reference for the user. I use lighter cables to connect to the positive red jack. I usually use a darker cable to connect to the negative black jack. The electricity flowing through the cables does not care what color cables you use. Now let's connect the cables to each side of the resistor and turn on the power supply. Now the display shows I have 4.56 volts coming from the power supply. Notice the current no longer displays 0. Now the display shows 0.002 amps. At the lower end of the current meter, this instrument is very imprecise. The current could actually be 0.001 or even 0.003 amps. Do not take the current meter to be very accurate at the lower end of the range. Now when I adjust the voltage and increase it, you will see the current does increase in accordance with Ohm's law. Since I have roughly a 1000 ohm resistor and I'm applying roughly 10 volts, I would expect roughly 10 milliamps of current. Again, this is subject to some inaccuracy. We've explored this device's features in mode 1. Now let's get acquainted to the feature of this device when we set it to mode 2. I'm mainly covering mode 2 just in case you accidentally activate it. This will help you identify if you are in mode 2, its features, and how to get back to mode 1. To activate mode 2, press and hold the current and voltage knob for a few seconds. When you do that, you'll see 3 LEDs illuminated. One under CV, one under the ones position in the volts, and one under the tenths position under current. When those 3 LEDs in red are illuminated at the same time, that means you're in mode 2. In mode 2, you can immediately change the voltage without pushing the voltage knob. Notice how when I turn the knob, the voltage output immediately changes. To change the digit position, you only need to push in and release the voltage knob once, and the LED will move left to right to the next digit. See how I click and move the LED until it is under the tenths position, and click it again until it is under the hundredths position. Just like in mode 1, you can inadvertently move the LED to the tens position and quickly get close to 30 volts. These resistors are 1/8 watt resistors. How much power can you safely apply to a resistor such as this? If I apply 16 volts to this resistor, it will get very hot to the touch. If I apply around 26 volts or greater to this resistor, there's a good chance this resistor will catch fire. Catching your breadboard on fire is bad. Catching the lab on fire is very bad. Catching the School of Engineering on fire is very bad. Catching Auburn University on fire is very bad. In short, fire bad. Don't risk burning down Auburn University. At the very least, this resistor will be hot to the touch and burn your finger. I don't want you to operate this device in mode 2. There is not enough safety features. If you turn on the power supply and it is already in mode 2, I want you to be able to recognize this so you can change it back to mode 1. I need you to be aware of mode 2's features and potential risks. Click and hold both knobs. See the LED pattern change? Now you are back in mode 1. This is how the current limit and the overcurrent protection functions work. I currently have the voltage set to 4.51 volts. Now if we check our current limit, it's set to 0.3 amps. Again, this is the preset current limit, not the measured current. Now if I short the terminals accidentally, or if I have too small of a resistor connected, then it would be requesting more than 3 amps of current. I'll touch the positive and negative terminals together. That means I'm short-circuiting the power supply. When I do that, notice on the left the current is limited to 0.298 amps, which is approximately 0.3 amps. Notice on the right, the output voltage now displays 0 volts. This happened because I short-circuited the output, and as expected, the device turned off the output voltage. This is a nice safety feature. This demonstrates I cannot supply more than the preset current limit. But there is another feature of this instrument that can cause some confusion. That is the OCP, overcurrent protection. If you look at the markings at the current knob, you'll see push and hold OCP on off. This is referring to a second level of protection called OCP, overcurrent protection. Now if I press the current knob and hold, you'll see an LED over the OCP, overcurrent protection. In that mode, if I exceed the current limit, it will disable the output of the instrument. Now let me demonstrate what happens. I'll connect the two alligator clips, which short circuits the instrument. You'll see the LED over the OCP, which means the overcurrent protection has been enabled. It's showing 0.3 amps, the current limit. Immediately you see two things change. Current display shows 0.3 amps, the preset current limit, and the constant voltage light goes out, but the OCP light is still on. This means the output of the front panel has been disabled. The output cannot be re-enabled unless you turn the power off and back on again. That means push the big blue button to turn it off, then push the big blue button again to turn the device back on. Some people have activated this safety feature and not been aware of it. They will be curious why there is no output from the power supply. If you see the OCP light is on and the CV light is not on, that means you have to turn the whole device off. Since OCP has been activated, you see the 0.3 amp limit and you see 4.51 volts. But that is not the voltage coming out of the terminals. To get an accurate reading, you need to turn off the main power and turn it back on again. That means pressing the big blue button to turn off the power, push the big blue button again, and this will turn the device back on. When you are finished using the power supply, make sure to turn off the power. Also, disconnect any cables that are connected to the front panel. That way the device is safe and ready for the next person to use.